So 2.1 was all about sets and set operations. Um, when we talk about sets, we use this kind of notation, and I'm going to use the first example here as kind of a notational guide for us. U generally stands for the universal set. It's usually a capital U. Is going to be the universal set. And the universal set is going to represent pretty much everything in the scope of the question or the example we're looking at. So everything in scope of problem. So if example one tells me that the universal set U is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, those are the only things that exist in this example. Okay, so sometimes the universal set is the set of all integers or just numbers 1 through 10 or all real numbers. So the universal set is going to switch between problems. But when you're working on this problem here, universal set is everything in the world as far as this problem is concerned. Um, we use these curly braces to represent set notation. So anything that goes between the curly braces is going to be elements in a set. And then we generally use capital letters uh, A or B, etc. Capital letters represent sets. And then for the notation, we use these curly braces to open and close set notation. So let's talk about some definitions here. The cardinal number, the first definition here that we see, we use this lowercase n as to signify the number of elements in the set A. So if I do, if you see n parentheses A like this, that's asking you for a number, right? And the number that it's asking for is the number of elements in A. So if we're looking at like this example here, and we're trying to do n of A, that's going to be the number of elements in this set, and all you do is just count how many things are in here. The actual content of the elements don't matter. It's just the number of objects that are in there. They could be numbers, they could be letters, they could be names of people, they could be phone numbers. Whatever these objects are, each one is counted as one object. So elements are just the things separated by commas. Next thing we're going to define is the complement, which will either use the apostrophe, a apostrophe, or a with a superscript of C to denote the complement of A, or the complement of a set. And this is the set of elements in the universal set that are not in A. So remember, the universal set is everything that this problem is concerning. So if I'm going to do a complement, for example, on number 3, we're saying everything that's not in A but is in C. So we don't want any of these, but we want everything else that exists in the universal set. That's what complement means. As far as do I want to do separate pictures for all of these? I guess we'll do some pictures up here. So a complement, or a complement like that with the apostrophe, we'll do a little picture for this. I'll do it with 2 sets, but you can generalize it to be a 3 set intersection. So we'll have sets A, sets B, and the universal set to kind of mirror this example that you're working on here. So there may or may not be some overlap between A and B. If we look at this example here, are there any elements that are in both A and B?
3 and 7.
Yeah, so if we were like putting all of the elements in this picture here, we would put like 3 and 7 on the intersection, and then anything that's not in the intersection and is in A would go. Actually, let's actually draw this picture. Let me draw this bigger here. So if we're drawing a picture of this specific situation, I would do something like this. Do A and B, and then the box that we draw is going to be signifying the universal set. And then as we're putting elements in, I know 3 and 7 are both in A and B, so they must be in that middle area there. That's part of both A and B. And then if I look at the elements of A, I've already put 3 and 7 in A. So A is all of this, right? So we see that 3 and 7 are already in that red circle. So I need to put 1 and 9 so that A has all 4 of its elements. And then B is also supposed to have 4 elements, such as 8 and 10 would complete all of B. And then if there's anything outside of that we didn't account for in the universal, we would put those outside of this 2 circles, right? We're going to put that out here in the universal set. So what's left over? 2, a 4, a 6. Is that it? 2, 4. Oh, 5 is missing as well, so we'll put 5 out there. 7, 8, 9, 10 are all in the box. Okay, so then this would be a representation of what's going on with these 3 sets given to us, right? So you can get an idea of how to draw a Venn diagram for these given sets. When we talk about a complement, I'm going to specifically just talk about it here and not necessarily, I'll just show it to you on the Venn diagram, but I'm not going to leave it on there, so pay attention. A complement is talking about everything outside of A. So if I draw a circle for all of A, and I shade outside of that, that shaded area is a complement. So that's a complement. Okay, so it's everything outside of A. So if we're trying to actually figure out what the elements are outside of A or in A complement, we would say don't include anything in here, just take everything outside of A. Okay, so that's A complement. The intersection of A and B, denoted by this upside down U shape, also called a cap, is going to be the set of elements that both sets A and B have in common. So the intersection of A and B, denoted by that symbol, is going to represent this area in between where we have an overlap of A and B. So that would be, in this case, that would be the 3 and the 7. Right, so an example of how we would write an answer for one of these, part number 5 in example 1 is asking for the intersection of A and B. When it's asking for, what it's asking for here is it's asking for a set. Unlike parts 1 and 2, parts 1 and 2 are asking for the number of elements in A and the number of elements in B. Here you don't see that little n in the parenthesis, which means this is asking for the actual set. So when we give this answer, we have to use the curly braces and list the elements that are in the intersection of A and B. So what are the elements in the intersection of A and B? What elements?
7.
Yeah, 3 and 7. This is the same question I asked earlier. What do they have in common? That's the same thing as asking what is the intersection, right? So 3 and 7, that is how we write the answer to this question, right? This question is just asking what is the intersection of A and B, and the answer is a set, right? You have to have the curly braces. You have to have the elements listed separated by commas. If you don't follow that notation, you will lose points on an exam. Next thing in the list of definitions is a union, which we use the symbol U symbol for this. Now don't confuse this U symbol with the universal set U. The universal set is a capital letter U, whereas this one is more of a symbol, a U-shaped symbol, also known as the cup symbol. If you can't tell the difference, you need to look closer at the symbol versus letter distinction. The union of two sets is the set of elements in A or B or both. So how the union works is we just group all of A and all of B together into one big set in the red outline, and we just name everything in that big grouping. Okay, so we kind of just merge A and B together. So here, if we were writing the answer for this, A union B, we would just list everything in the merger of A and B, right? So we take A and we merge it with B. How many elements are in there? 6, good. And then we're just going to list them. It doesn't really matter what order you list them in. To make it easy to read, I'm going to list them in increasing order. But sets don't have any kind of ordering to the elements. So you can put these in any order you want and it would still be the same set, right? There is no inherent order to things in a set. Just like, because I can just put them in a circle like this and just list the elements, right? And there's no specific area, or I don't need to put them in a specific order. As for the cardinal number rule, this is just an equation that helps to not overcount. So this equation ensures that we don't overcount things. And what I mean by that is if I wanted to find how many elements are in A union B, for example, you might think, oh, let's just take the number of elements in A and the number of elements in B and add them together. Because remember, we're just merging them together, right? So if I took all of A and all of B and I added their number of elements together, what happens is I take, there's 4 elements in here and 4 elements in here. So if I add those together, I get 8, right? So it seems like the merger should have 8 elements. But we just saw that when we actually merge them together, not counting duplicates, like we wouldn't count these ones twice, right? Because we're merging, we're not just like adding blindly. These are the same elements that exist in both A and B. So if we actually merge them together doing this, looking at this picture, we saw that there was 6 things. So this formula here removes those elements from being counted twice. So we do add the number of A and number of B together. We do add the 4 and 4 together to get 8, but then because we counted these guys twice in that sum, we're going to subtract the intersection once. So the number of elements in this intersection, since they get counted twice, we need to subtract that number once so that we go back to just counting them once. So we'll count these guys, and these guys exactly once as a result. Okay, so this just make sure you don't make that mistake of just adding blindly and counting certain things multiple times. Mary, are you asking about? I'm not. Well, are you asking about these numbers out here? Okay, those numbers came from. We need to put every single thing in this universal set in this box here, right? Overall, so I put everything in A and B where they belong in these 2 circles, and then whatever was left over, since they don't belong to A or B, I just put them in the box. We just don't put them inside of either of these circles because they don't belong in sets A or B. Okay, so these are just the extra numbers that were in this universal set. Any other questions before I move on from this stuff? How did you find... Are these ones are given to you in the question. They would have to give you the sets for you to be able to do something like this. Yeah, usually you're going to be given sets to work with. Even if they're not like nicely written like this, like if you look at the next question, in example 2, it's more of a word problem, but you can kind of figure out what different sets are. So it says 1,000 people participated in a campus blood drive survey. That seems like the whole universal set. So the universal set is going to have 1,000 elements in it, which is just everyone that participated. And then we have different breakdowns of students. So 490 willing to donate blood, that's one set. 340 willing to help serve a free breakfast, that's another set. And then 120 students willing to do both. Since they're willing to do both, that both kind of makes it sound like an intersection of two sets. So as you can see, you have two sets here. We're going to label these with the sets that were given in the question. This both is not going to be a third set. That's just going to be an intersection. So we'll label these as like donate blood, the donate blood set, and the free breakfast set. Right, and then the universal set big box around the whole thing would be like the survey participants. Would be the whole big square set. Okay, and then you're going to do some number manipulation in this problem. I'm going to leave you guys to actually work your way through that one. But are there any other questions on anything so far? Okay, so when I'm going to go over a bit of the things. For the cardinal number, you just list the numbers. For the cardinal number, you count the number of elements. So you're not listing anything for the cardinal number. It's just a single number answer. Just how many things are in this set. And I'm saying things and elements specifically because while like these are numbers in a set, they don't necessarily have to be numbers, right? These could have been like A, B, C, D. That set would still have four elements, right? So I don't want to say count the numbers in the set. It's count the elements or count the things that are inside your set. Okay, let me actually talk a little bit about the 2.2 handout because this is going to be where we do a more involved activity. So I'm going to actually do one of these for you so that you see an example and then you're able to work on them on your own, hopefully, or with the TA in your group. We need the workbook to be able to do this, so let me go grab one of these guys. And put it here. Why is it doing that? Okay. So you're going to work on this in your workbook. Actually going to need more room than this probably. So do I have more room? Okay, we'll work with this one here. So I'll kind of scroll back and forth so I can put numbers in that diagram up at the top. So, question tells us that 23 bears go to college, and the following is a result of how many are taking math, English, and history. We want to draw a Venn diagram to show this information. I guess I could just draw one here. to make life easier. We have 1, 2, and 3 circles. Right, and we're going to label these with the different classes that the bears are taking. So we're going to have M for math, E for English, and H for history. So all of the bears that are taking math would go in the math circle, English would go in the English circle, and history would go in the history circle. Now, obviously, these bears are not going to be just taking one class, or maybe some of them are, but some of them are going to be taking multiple of these classes. So a bear might take math and English, or math and history, or math, English, and history. This kind of diagram shows you all possible combinations of those 3 classes. So if a bear is in this region here, what classes would he be taking?
English and history.
Perfect. This region represents English and history. Now, instead of putting individual dots in here to represent bears, which is what we could do, we can also just put a number in here for how many bears are in each region, right? And the best way to fill out something like this from given information is to work backwards. So work from the smallest area to the largest area. The smallest area in this Venn diagram will be the bears that are taking all 3 classes. And that region would be the intersection of all 3 circles, right? The intersection of all 3 circles would be the centermost area in here. So how many bears are in this area? 3. So we'll put a number 3 in there in the middle. And that's where we're going to begin, because we have to work from the smallest area to the larger areas, because if we start with, let's say we didn't put that 3 in there, right? And if I wanted to start with this area, or actually not even that area, let's say I start with the English and history bears, right? Bears that are taking English and history. In my Venn diagram, that is represented by this football-shaped area, right? And I want to put the number 4 in that area. But those 4 bears could be just taking English and history, or they could be taking math, English, and history. We don't really know how these 4 bears split up into these 2 areas within this area. Right? So same issue happens with, like, if you try to start at the top here. I know that there are 13 bears taking math, which means there are 13 bears in this circle, but I don't know how they're distributed into these 4 sections. Does that make sense? So in order to figure out how they're distributed into here, we need to start with something that is just a single area, that is not made up of multiple areas, which is why we start at the bottom here with this region, which is a single region on its own, and we'll put the number of bears that go in there to begin. And then we're going to work our way up this list to figure out more and more areas. If I have, like I said, I have 4 bears taking English and history. That means there needs to be 4 bears in this total space. And this total space is made up of 2 regions, which means how many bears are going to be in this region? 1, exactly. So that the number 4 doesn't show up directly, but this area should have 4 bears in it. Right, so far we've placed these 4 bears. Next we'll look at the math and history bears, which apparently there are 6 of. So we find the math and the history circles, which is all of this and all of this, and we're going to look at their intersection, which would be this total area. So if there's going to be 6 bears in this area, and I've already allocated for 3 of them, that means we're going to have 3 in this area. Good. I see people answering before I ask the question, but that's good. So that number 6 is accounted for, right? We see the 6 total with 3 and 3. The next one is going to be the 5 in the math and English region. the math and English region would be this one here. So if there's already 3 of them here, how many do we put in the rest of the space? 2, perfect. And now we can move on to the bigger circles. So now if you take any of these circles, like English for example, remember the English circle is made up of 1, 2, 3, 4 regions that it's broken up into, right? And 3 of the regions we have numbers for. If we just add those 3 regions together, we see that we've accounted for 6 bears, right? 3 here, 2 here, and 1 here. That's a total of 6 bears. But we know that there's supposed to be 10 taking English, which means good. We're going to put 4 out here so that when we look at the total of English, which is all of these numbers together, that should match what we're seeing over here for English. And we're going to do the same thing for history and math. History already has 3, 6, 7 members or 7 bears associated with it, but there's supposed to be 10 total. So we're going to have 3 more bears in the history. And then finally for the math, we have 3 plus 3 is 6 plus 2 is 8 bears. And we're supposed to have 13, which means we're going to have 5 more. Good job. So we've accounted for the math, English, and history numbers as well. There's one number we have not accounted for yet. Does anyone know what number I'm talking about?
The 23.
The 23. The 23 bears. I know it's like in the beginning of the question it's kind of hidden, but we have to account for all 23 bears. That's why we have this box around the math, English, and history. This box just represents all 23 bears that are actually going to college right now. So whatever we didn't account for in here in the math, English, and history classes, because maybe there's bears that aren't taking any of those classes, right? And those would be out here in the box, not necessarily in these 3 circles. So we need to add all of these up and then figure out how many bears are left over to place out here. I'm seeing 2s. 5, 7, 11, 12, 15, 18, 21. So there's 21 bears accounted for in this area. That means there are 2 bears, and those 2 bears are not taking English, math, or history. Nor history, I guess. Are there any questions on how I got any of these numbers before I stop going over this?